Double checking, your audio is working. All right. Okay, so let's start off with a question that George asked. Okay, you guys ready to go? All right. So let's start with a question that George asked. I think there are two questions, and they're really good questions. The first one started off as a question about whether you can convert any algorithm using loops into algorithms only using recursion, and the answer is yes. Okay, so anything that makes use of a loop can be converted to use only recursion, and the other way around as well. So any recursive algorithm without loops can also be turned into iterative algorithms without using recursion. In other words, recursion or not, as long as you have a way to do repetition, it is considered equivalent. So that's the first thing. The second one is there are problems that are impossible to solve, as opposed to intractable, which means it takes a long time to solve. So we'll start off with let's see. Let's start with VLC, and I think I solved the problem of the scaling issue. So I think we can actually take a look at the document camera correctly these days. Okay, it's almost there. You just have to rotate it a little bit. It doesn't remember the rotation, so I just have to do that part here. Question? No. Okay. And I think you just have to do the.
Professor Tech, don't some programming languages implement recursion differently that makes it more efficient?
Yes, in terms of efficiency, there is the constant difference, which means recursively, most algorithms are inefficient in the recursive format because recursion involves subroutine calls, and subroutine calls involve pushing a whole bunch of stuff and popping a bunch of stuff. That is more than what you need to do if you maintain your own stack. So it is correct that if you turn an algorithm into a recursive format, you lose efficiency. On the other hand, most recursive solutions, as long as the problem itself is recursive, the recursive solution is a lot easier to read and understand, as well as to prove it is correct to validate, compared to the iterative version, because you have to implement your own stack, basically, and you have to, so there's a lot more to the verification or the validation of the correctness if it is not recursive.
But don't some programming languages modify how the stack works in recursion?
Yes, it's called tail end recursion.
Yeah.
So if it is a tail end recursion, it basically turns it into a loop where there's no call and no return, so that you don't have the extra expense in terms of resources when you have the recursion at the very end of the whole thing.
Which programming languages do that?
The tail end recursion optimization is Prolog.
That's the only language that does that?
I think Lisp may do it. I'm not 100% sure. We can look it up. Lisp is interesting because both Lisp and Prolog do not have loops. So the only way to do loops is to do it recursively. In the case of Prolog, okay, how many people still remember Prolog? Because we did talk about Prolog in this class. It's about predicate logic, right? So the tail end recursive version of Prolog is to say, a particular predicate is true if and only if blah, 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 and then the last one is that the predicate that you're defining in that clause. So that's how you can do Prolog recursively. But if it's a tail end recursion, which means nothing is following the recursive call to the predicate itself, then you can actually implement it as a loop because there's no need to come back. Because the only thing you're going to do after you come back is what? Is to go back to to a previous level. Okay, so there's that. Let's see. Well, see, one of the best use of AI is to have a mic that can automatically cut out all the well, that sort of thing. So all that stuff will be cut off, not getting recorded at all. That would be an awesome application of AI. All right, so I think this one does scale correctly now. Yes, excellent. Okay, so I'm going to use this as my little whiteboard. I'm just changing the exposure. There we go. windows. I can hear that. All right. So to answer George's question, okay, there is a whole class of problem called NP-complete problems. Okay. So the big question is, and I think we have already touched on this, that the traveling salesman problem is in that class. Okay. And NP-complete is a very interesting class of problems because every problem within that classification, they can all transform to each other using polynomial time. Okay, which is great because the next time when you are hired as a developer and you are presented with a problem and you say, hey, this is a problem with, I don't know, optimizing the use of registers in a compiler or optimizing the use of real estate on a chip, in terms of silicon, gates and stuff like that. Usually it is some kind of optimization problem. So if you can relate the problem that you need to solve and you say, hey, I can transform this problem that I need to solve at work so that it becomes the traveling salesman problem, and the transformation itself is only going to take polynomial time, which means if the problem size is n, the transformation itself is big O of n to the power of some fixed power, okay? Then your problem is also in the class of NP-complete, which means it is an intractable problem. There are no known algorithms to solve those problems effectively. But they can be solved. They just take a long time to solve. Yep.
So for polynomial time, that's just any power, n to any power?
It's n to any fixed power. So n to the power of 30 is still polynomial. It is not good, but it is still polynomial time. There are much worse things that can happen than n to the power of 30. Like n factorial is really bad.
Or n to the n power?
N to the power of n, that might be worse than n factorial.
It is.
Yeah. Okay. So, but I do want to kind of point out what is the p and what is the n in NP. P is actually polynomial. Polynomial. And the n part, okay, let's explain that part first. Because this seems contradictory. Because I said NP-complete problems typically has an n factorial in it, in the time complexity, and yet NP, the description, has polynomial. So the trick has to be the n. N is not. Okay? In other words, NP is not polynomial. Okay? The n stands for non-deterministic. Non-deterministic. I think I can actually write better on a piece of paper than on the whiteboard. Has to do with the traction thing. Okay. Non-deterministic means you can start, using today's technology or today's term, non-deterministic means you have an unlimited number of cores. You can start up any number of threads and they can all compute in parallel with no penalty. That's what the N stands for. But if you think about it, that's a big deal. Because instead of having an 8-core i7 processor or having 4 of those on the same motherboard, you have an unlimited number of cores and they can all operate in parallel with no penalty whatsoever. So the traveling salesman problem falls into the NP-complete category because I can start one thread to look at each and every permutation of all the destinations. Then it becomes just linear. Because if I have n destinations, then each processor, each thread, only has to add up the cost for that particular permutation of destinations. And then I need one more to compare all of those, and that'll be the end of it. Question?
So you're saying that you have a thread for each route?
Yes.
Okay. And then those threads never need to share information, right?
They can share information that does not incur any cost. Now, if they have interdependency, then you have a problem. But since that problem can be truly parallelized, in other words, if I have 120 routes, because 120 is 5 factorial, okay? So if I have 5 destinations and I have 120 people to help me out, I can make 120 photocopies of the map, and each person can work on a different route, and they can all doing computations in parallel. And even for the result, I can still get the result, kind of in parallel as well, because I can, I do have to compare 120 possible results, But the comparison can also be the log of n factorial, because two people can come up with the best route between those two, and then I can just kind of like a tournament, then I can get to the shortest route pretty quickly. Okay, so that's NP complete, and you will see this again for those of you who are moving on to a computer science degree. You will see this again. This is a pretty big topic in computer science. But NP complete is bad in terms of time consumption, but the problem can be solved. Okay, there are known algorithms to do it. It just takes a long time. But there are problems where you cannot solve. I think it's called Turing's theorem. And let's take a look at, just take a quick look. Turing's theorem. Okay. It's also called the halting problem, which is, I'm not going to explain too much of that, because the halting problem has to do with whether a Turing machine is going to go to the halt stage, which is a conclusion. And the halting problem means for certain problems, you cannot find a Turing machine that can actually halt. In other words, it'll be inconclusive. They can never really stop computing. And the Turing machine is already the most general class of machines that can model everything that we can make so far. Okay. So we'll just take a quick summary of this. Importance and consequences. It's one of the first problems to be solved, undecidable, and subsequently many other undecidable problems have been described. The typical method of proving a problem to be undecidable is with the technique of reduction. To do this, it is sufficient to show that if a solution to the new problem were found, it could be used to decide an undecidable problem by transforming instances, blah, 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 blah. So it's the same technique is used to demonstrate that the problem is NP complete, only in this case, rather than demonstrating that the problem, there's no solution, it just takes a long time. So there are two different problems. Okay, one is NP complete, which means we will get to the halt state at some point. It just takes a long time for a regular machine. But if you have a magical machine that has an unlimited number of cores, then it will just take polynomial time. But we also have the problems that cannot stop. So those will fall into the halting problem. Okay, so you will get to know what is a Turing machine, what is a stack machine, and what is a finite state machine. Those are all different classes of abstract machines. When you get to take either it's called computation theory or automata theory. So those are the classes. Those are upper division classes in a 4-year university. Some of you, if you enjoy this class, you will love those two classes. I'll just put it that way.
The Turing test is different from the Turing.
The Turing test is a whole different thing, because Turing was a smart guy. So he came up with all the mathematical stuff, all the rigid proof and stuff like that. But Turing test is kind of his idea of what is considered intelligent. So the Turing test has several variations as well, but they all revolve around the same concept of whether a computer can imitate a person well enough that you cannot tell that, oh, it's actually not a person on the other side of the line. We are coming pretty close to that with Watson and with Siri and also with Google. I would say some people would talk less intelligently than those resources.
Yeah,
okay. So I would say we have come a long way, and Turing would be impressed if he were to jump in time and come to today, from the 50s. He would be impressed how close we get to making machines intelligent or appear to be intelligent. Okay, all right. So that's kind of like a sidetrack, but I do want to go through the sidetrack because I think it is kind of important, in the long run for computer science. Okay, so with that out of the way, what we'll do today is to do some practice tests, because next Tuesday we'll have exam number 2. Well, if I don't do exam number 2 now, then we'll have the final exam carrying 60% of the grade, which is probably not a very good idea either. So I would much rather have a second exam, which is going to overlap really a great deal with the final exam, so you can kind of look at the second exam as a really good warm-up for the final exam. But still, we are distributing the points a little bit more evenly that way. So we'll take a look at the practice test. One practice test has been online the entire time, so some of you might have read it already. The other one I just posted earlier today, so that one is new to everybody. So I just look at exam 2. I cannot find it.
In recursion.
I cannot find it because they're under the smaller topics. If I turn on editing, I can actually find it a little bit more easily. Yep, they're under recursion. So this is the actual practice exam for spring 2015. The other one is the actual exam for spring 2015. So they're very similar in terms of what type of question was asked. We'll take a look at the first one, which is a link to a Google document. I think all of you can probably follow that. I think I'll open this document for everybody to look at. Yep, I can see all these. Yeah, yep, definitely. Okay. Do you get to choose those icons? No?
I
Okay.
wish.
You wish. Even more. There you go. Keep going. All right. So question number 1 is something that we have seen already. I talked about it briefly. The homework assignment is actually a lot more difficult than this one. So we consider a class of 30 students. Express the chances of at least 2 students having the same birthday, just the month and the day of month. You can use C for combination, P for permutation, and the factorial symbols in the final answer, along with all the other usual symbols like division, addition, and stuff like that. And do this in steps. Okay, and the chances of no one in the class of 30 sharing a birthday is the other question. Okay, I think that's actually the question for the exam itself. So we'll solve the first problem first, okay? So at least 2 students having the same birthday. How would you figure that out? Now, how do you approach this problem? That's the first thing, okay? Let's not even worry about the numbers. Let's think about what do we mean by the chances, okay? Because that's the first question. The probability, very good. So the probability, but how do we compute probability? It's a division, okay? We know it's a division of some kind. What are we dividing? What is the numerator?
The chances of the possibility that there are.
The number of outcomes, okay? So the numerator is the number of outcomes that we are interested in. But I'm just going to say the number of, okay, number of interested outcomes or outcomes of interest, okay? Divided by the number of all outcomes, exactly. All possible outcomes, okay? So this is important because, knowing what quote-unquote chances are is really a fraction, which is the numerator is the actual number of outcomes that we're interested in. So it has to be a natural number. It can be 0. It can be all the way to the same number as the number of all outcomes, but it has to be a natural number within that range. The denominator has to be the number of all possible outcomes, which we also know as the cardinality of omega, okay? Because the omega set is used in this particular context to represent the set of all possible outcomes. Are we still doing okay so far with this, okay? So with 30 students, okay? So with 30 students, the denominator is actually fairly easy to compute, okay? Because we just say, all right, with 30 students, the first student has 365 days. Let's not take leap days into consideration, okay? Because that really kind of complicates things a little bit. So we'll just say there are 365 days. The first student has 365 choices. What about the second student? 365, okay? Because we are looking at the number of possible outcomes, okay? So unless you're talking about the class of twins and triplets, or you place special restrictions, like if you are by yourself, you cannot come to this class, you have to take this class with your twin or triplet, then the consideration will be different, okay? But on the other hand, if we have no general rules of who can enroll in this class of 30, then the birthdays become completely independent. Which means if one person picks one particular date, the next person can be any day in the year. Can be the same, can be any of the other 364 days. So that means the total number of outcomes as far as a class of 330 students are concerned is 365 to the power of 30. Is that making any sense?
Oh, because there's 360 possible ways we can.
Exactly, because the birthday of each person is independent from the birthday of everybody else. So the key word here is that they're independent. In other words, if one person says, okay, I was born on the 5th of July, okay, well, the next person can have the same birthday or some other birthday, has no relationship whatsoever, and there's no restriction placed on the birthday of anybody else. Yep.
At some point, would we be able to look at like a twins or triplets restriction, like in this class? Just
Sure. Maybe after we get this
Yeah.
whole exam through, then we can go back and take a look at that one. I haven't really thought about it, so I'll be working on the problem as we go too. Okay. Okay, so that's the denominator. It's pretty easy to work out. What about the numerator? What is what are we dividing by this particular number? Now the numerator is the number of outcomes of interest. So we have to read the question again and read it carefully. We want to look at the chances of, okay, this is the key word here, 2 students having the same birthday. Okay, and that's just the month and the day of month. But the key here is 2 students having the same birthday. Okay, so that will put the restriction on 2 specific students. Yep, go ahead.
So if that would be permutations, right?
Combination?
Would it be combination?
No.
The combination.
They're
Because it has to
related.
be.
I did not say which 2 students.
So ordering does matter.
Hmm?
Then
Sorry?
order doesn't matter then, right?
Order does not matter.
Okay. Then
So in a class of 30, there are 30 choose too many ways to choose 2 students and say, okay, let's think about these 2 having the same birthday, right? But once we pick the first one, then the second one would have the same birthday, which is a restriction. So now we have the restriction. We lock one birthday, the other person would have that birthday as well. The other person cannot choose anymore. Okay, but the rest of the class, the other 28 students, can have any birthday because I did not say exactly 2. I said at least 2. So it is possible that the entire class has exactly the same birthday. That would still fit the requirement of at least 2 people having the same birthday. Is that? Go ahead.
Never mind.
Okay. So going back to the math of this. Okay. So we'll work out this part first. Okay. The first person picks out any one of the 365 days. Not a problem. The second person has no choice. Okay. If we say, okay, out of these 2 people, I want them to have the same birthday, the next person has no choice, so there's only one possibility for the next person. What about the rest of the class?
364 to 28.
Okay, the rest of the class has 365 to the power of 28.
shouldn't it be 364?
Nope, doesn't
No,
matter.
it's 365 because there's no restriction. I said at least. Yep, go ahead.
Can we do that one more time?
Do it one more time. Okay. So the first person, okay, of the 2 that must have the same birthday, because each outcome of the numerator is a pattern where 2 people have exactly the same birthday. So out of those 2 people, I say, okay, you're the first one, so you get to choose the birthday. The second one that is supposed to have the same birthday doesn't have a choice anymore. Has to be the same as the first one. So that's why we have a 1.
Oh, you're forcing the favorable. I was thinking of doing it with complements instead. So, but you can force the favorable one and then let everyone else do what they want, right?
Right. The rest of the class, the other 28 people in the class can now say, oh, okay, we can choose any birthday because I said at least 2. I did not say exactly 2. So the answer turns out to be pretty easy because this is 365 to the power of 29th. So the outcome turns out to be 1 divided by 365. That doesn't look right to me. Yep.
So if it was all everybody having the exact same birthday, then that would be that would just be 365, because it'd be 365 days that everybody could share. So it'd be
Correct.
365 over 365 to the 30.
Correct. Yep. But I'm looking for the chances of at least 2 people having the same birthday. This doesn't look right to me.
It would be 1 minus, 1 over, 1 minus that answer right there, because it's the opposite case.
No, this meets the requirement. Yep.
We could also do it by inverse, right? Where we find the probability of no one sharing the same birthday and then 1 minus that.
Oh, that's right. Okay. No one having the same birthday. I think that's the better way to look at it. Thank you. Okay, so that one is now that one does have a lot to do with permutation. Okay. What are the chances? So what are the chances? Well, we'll come back to this one and see what exactly does it represent. Okay, because I'm pretty sure it does represent one thing. Okay, but we will solve the problem using the flip way, which is to look at the probability of nobody in the class share the same birthday, which means everybody has a different birthday. Okay? If everybody has a different birthday, what are the number of outcomes for that particular case? The first student has 365 choices. But once the first student picks a particular birthday, the next person only has 364 choices.
Isn't that 365 factorial then?
Divided
Nope,
by
it's not quite that either.
Because you're only going to 30, you're not going all the way down.
Because you only have 30 students. Okay? So this becomes something that we,
365 factorial divided by 365 minus 30 factorial.
Or isn't that just?
which is also known
365
as
choose 30?
combination.
Yeah.
We are choosing 30 out of 365. I think it's supposed to be written the other way.
365
Yeah,
365. Out of 365, we choose 30. Okay, so that's your numerator. So if you do a 1 minus this number divided by 365 to the power of 30, that would be the probability of having at least 2 people sharing the same birthday, which is actually pretty high. Does anyone want to run the math? I can do it.
Let's do it.
I'll run the math. Okay. So okay. All right. So the first number is going to be come in 365 choose 30. And then the second one is going to be power 365 to the power of 30. And we want to figure out what is the fraction. Okay, so A1 divided by this one. This is representing the chance of everybody having a different birthday in a class of 30. That's a pretty low chance.
Yeah.
Which also means the chances of at least 2 people in the class of 30 having the same birthday is really close to 1. But that's actually does make sense. Yep.
What was our other answer, 1 over 365?
Yeah.
1 over 365? Okay. That's a good question. So let's go back to this one here and figure out, okay, what is wrong about this?
What we're missing in that one
Mhm.
is those other 28 people can have have the same birthday. So if that's true, the cases that aren't represented here would also be true, right? Because we're only checking, like for instance, if me and Ian had the same birthday. That's the chance of me and Ian having the same birthday. And everyone else we don't care about.
Okay. I think it is missing the fact that, okay, this is supposed to reflect the number of possible outcomes, right?
Yeah, that would be the
It's
odds that it's just 2
1.
people, because you don't get a choice of your birthday, it's already chosen, and there's 365 days for the other person, so the odds of them having your birthday is 1 in the 365.
Right.
But over the entire class, then it would have to grow.
Correct, because we have to now pick any two people for one to be the first and for the other one to be the second.
And the more people, the odds should increase as you increase people.
Yep, go ahead.
I was looking at this problem and I thought maybe of approaching it similarly to how we did the homework, where you find the probability of exactly 2 people sharing a birthday, and then 3 and 4 all the way up to 30, since it's 2 or greater. Is that incorrect?
It's a little bit different.
Okay.
Yeah, this one is a little bit different because it's not a sequence anymore. Yep.
We did it for one day based on that. Like every day has that possibility. We will have pretty much multiply by 364 to get to that, because every day has the possibility, or for every day we can have the possibility of 2 people having that date as a common birthday.
What are you talking about?
I'm talking about 1 over 365 that we got the first time. We still need to multiply by 364 to get to where we want.
That would just make it bigger.
Well, that will make it bigger. We do want to make it bigger, but not like that.
Because we randomly pick one day based on that. So we go for each day, and say day 10, 365. This is the possibility of 2 people having that birthday. So that probably turns throughout the year. So for each day, there is that portion of probability that 2 people will share.
I think the problem with that one is it only takes into consideration of, okay, so let's name people in the class, okay, because that will make it clear. Let's talk about the class of only 5 people. Okay, so we only have 5 people, and instead of naming those five people, we just call those A, B, C, D, E as students. Okay, so what that is representing is A has 365 days to choose from. Because A and B must have the same birthday, B cannot choose anything, only got one choice. So now, A and B are the ones that have the same birthday. Now C, D, and E, I don't really care because I'm only looking at A and B to have the same birthday. So these have 365, 365, and 365. Now there are several problems with this one. The first one is, but what if B and C, have the same birthday? What if C and D have the same birthday and D and E have the same birthday? We have 5 choose 2 combinations of quote-unquote same birthdays, but that's exactly 2, right? And then within C, D, and E, they can also have they can also have the same birthday too. And those are not taken into consideration. So that's why this way of counting doesn't work. But the other way around does work because using looking at the combination of 365 choose 30, that reflects the number of outcomes where the entire class do not share a single birthday. Well, what is the reverse of that? The reverse of that is at least 2 people share the same birthday, which is what we are looking at, what we're looking for. So is that okay? Yep.
On the Wikipedia birthday problem page, it shows it as for the complementary one, it does 365 permutation n over 365 n, or to the n, instead of combination.
Instead of combination, it is
30 it comes up with 70%
permutation.
instead of 100%.
Okay.
For n equals 30.
So let's see. So with permutation, so it's 365, 364, and we want it all the way down to 365 minus 29, right? And then we want this number to be divided by 365 to the power 30. So the top part here is that permutation.
No, it's a combination.
No, it's permutation. It is permutation because do you still remember what is the definition of permutation versus combination? I made that mistake once of confusing myself between permutation and combination. This is what I want to accomplish, which is actually permutation, but I chose the wrong function to apply, which is combination. Okay, so let's go through permutation again. Permutation of n choosing R is how many different ways can we arrange R things out of n things. Okay, that turns out to be n factorial divided by only one thing. N factorial divided by n minus R factorial. That's permutation. Combination, on the other hand, is how many ways can we choose R things out of n, but ordering is not important. Okay? So we start with permutation, okay, which is this number. And then we say, oh, but out of these permutations, there are exactly R factorial duplicates for each combination. Because out of one combination that has R things, there are R factorial ways to rearrange things so they become different permutations. So that's why there's the extra R factorial here. So so you're correct. So in the equation here, I chose the wrong function. So instead of using combination here, I should have chosen permutation, which is permut. And now it amounts to 70%, which is still pretty high. You know, there's a 70% chance that at least two people in a class of 30 sharing the same birthday. Now this class still has about 43, 44 students, so let's figure out the chances of at least 2 students in this class having the same birthday. So we'll just say 40, okay, which is going to be a little bit less. I mean, it's a little bit less than the chances of 43, but there's an 89, almost 90% chance that 2 students in this class share the same birthday, which is pretty high. All right. So are we okay with this? Yep.
I'm still confused where we have 2 different answers. The one over 365 and
That one is just wrong because I don't have a problem with that. Thinking that one is just wrong because it doesn't. First of all, it doesn't take combinations into consideration, and then the second part is it doesn't take duplicates into consideration either.
Okay.
Yep.
So there's almost a 90% chance that in this classroom of 40, 2 of us share the same birthday.
That is correct.
Well, let's find
Let's
out.
find out about this.
Yeah,
But that's going to take a while. You guys will have to write down your birthday on a piece of paper.
No,
and pass
just
it
make the
around.
Google Docs open, and we'll just punch them up right there, real quick.
But not everybody. Then you will only limited to people with access to a Google Doc.
Yeah, but the percentages should still be around 50.
Okay, if I get a piece of paper and we pass it around, everyone puts down their birthday.
Yeah, I
and then
think
at
putting
the end-
it on a piece of paper works a little better. So at the end of the class, we can just do that. Okay, so all right. So
Sign in
don't
sheet.
sign in sheet, but don't sign in. I don't need your name on it. I just need your birthday. Okay. And don't
Day of the month and the month, no year.
just day
You don't need that.
day of month and the month. Correct. Yes. Go ahead.
You could do it in parallel, make 4 lines.
Yes, that we can. But I have at least 40 pieces of paper. I can actually I can do the non-deterministic part of it too.
So many processes.
I almost matched you.
See, I think you guys are really getting the concept of this class because I can see how you apply it
I almost matched him.
in the class. Yes, go ahead.
Oh yeah, we almost had a match already.
Verbally,
It's that 10% gap.
But then you lose the anonymous part of the whole deal because I don't want people to know what day is a birthday. Yep, go ahead.
If you alter the complementary one, say at least 3 or 4, what
My
number?
birthday's in that class.
Okay, extra. Okay.
Which one am I supposed to do? Not always.
Oh, yeah.
you know what? It's not clear which one is which. Let's do that.
A question, with the way that student over there said about we could just use the inverse logic, does that one just represent where we're looking for two instances where they match? So if we were looking for 3, would we subtract it by 2?
Okay, that's a good question. I will address that one. That means see what the question is.
On the exam,
Yeah.
you don't want an answer, like a number, you just want an equation or a formula.
A formula, yes. Yep. A formula is better. Yep. Okay, so the question is, can we generalize this? Okay, the question is, can we generalize so that we can express the chances of at least 3 students having the same birthday, at least 4 students having the same birthday, and so on. Okay? So if you think about at least 3 students having the same birthday, that means you can still use the reverse way to do it, which is, calculate the complement first, and then do 1 minus the complement. Okay, so let's figure out what in general how do we express this problem. Okay. And I'm view only because I haven't signed in. Google account. Okay, I need to sign in first.
I think there's a fitting one.
Huh?
That way, as long as you don't times it, right?
How do we connect it?
Yeah, no, it doesn't matter.
Okay, so getting back to the document.
Oh, we got like 3 pages.
Refresh it.
We got one back. I want to count them.
Okay, so let's change the problem here, and so that it becomes chances of at least k people and having the same birthday. Okay, so that's the more general version, which also means it is not going to be likely that I'll be asking about birthdays again in the actual test. But it's not a bad idea to kind of think about it. Okay, so once again we want to think about a complement. Okay, what is the complement of at least k people having the same birthday?
Chances of
Less than k people, like 1 minus k people.
not K.
We use the same technique, okay? When we ask about a problem of at least 2 people having the same birthday, we think about, what if nobody shared exactly the same birthday? So when we think about at least k people having the same birthday, we think about up to k minus 1 people having the same birthday. Okay? So let's write it down. Okay? We write down the thinking process. Okay? We say, okay, so we look at the complement. The complement. I think it's the I because it's the opposite. It's not the praising, which is the E. Right? Okay. So the complement is going to be at most k minus 1 people having the same birthday, and that works out in the previous case as well, because in the previous case, k is 2, so the complement is 1 person having the same birthday, which means nobody shared the same birthday, right? Okay, so in this case, we want to calculate what are the chances, what is the number of outcomes where k minus 1 people have the same birthday. Now, the solution to this problem is actually on Wikipedia. So we can go through the whole exercise and then use Wikipedia to cross-check it. And as we speak, I know somebody is editing Wikipedia. Well, that's the greatest part of Wikipedia and also one of its weakest point. But that's actually when people don't know how to use Wikipedia and look through the edit history and say, okay, who did the last change? What is the credential of that person? All right, so how do we figure this out? At most k minus people having the same birthday, and we have n people to begin with. Well, it has to do with, factorial, permutations, and combinations. Last time, yep, go ahead.
K factorial for the denominator.
K factorial. No, the denominator is not an issue anymore. The denominator is always 365 to the power of 30. That's the total number of outcomes. That does
Right.
not change.
That's stupid.
Yeah.
So isn't it, well, yeah, N, we'll get.
Would it resemble the problem that we just solved though with like the factor or like the
Yep.
general numbers?
Okay.
So
So
would it be
is it-
like permutation 365, 30, or sorry,
Okay.
P of and
Okay, so let's start. Go
365
ahead.
P.
Okay. Let's start with the first person. Okay, the first person has 365 days to choose from. The second person out of the n minus k minus 1 people, because those are the ones who have unique birthdays, right? So we have 364 times 363 times blah blah blah. But the last number is going to be which one? I know it has to do with 365 minus something. Hmm? No, but now we are expressing in n and k, okay?
So your N minus
It has to do with both n and k, okay? Because n alone is not going to be useful because k has to be factored into this somehow, okay? Now we can approach this here really step by step and say, okay, what if n increases? Well, if n increases, we have to stop earlier, okay? And what if k is larger? If k is larger, we also have to stop earlier. Yep.
So n is the number of people or k is the number of people?
The class has n people,
Okay.
and I want to figure out the probability of at least k people having the same birthday.
Ah, okay.
So k was 2 in the previous case, and k is just generalized in this case. Okay. All right. So getting back to this one here, what do we use in this part, in this parentheses?
We don't subtract N minus one.
N minus.
No, it's minus K. Number of people.
Okay, what did we use earlier? Okay, we want to generalize from the previous case. So in the previous case, we want to know what are the chances that no one in class share the same birthday. So we go from 365 to 364 times blah blah blah, and all the way down to 365 minus 30 plus 1.
29.
Yeah, 29.
Yeah.
No, but that'll be.
Okay. And that one is significant. What is that one?
The individual who has his own.
That's our k minus 1. Okay. And what about 30? 30 is our n. That one is the k minus 1. So how do we generalize this? So we have minus n plus k minus 1. Does that make any sense? All right. And I know we can do some simplifications here. So we can move this n into here.
Where's that 365 minus 30 plus 1 coming from? Is that for the chance of nobody?
The number of outcomes where nobody in the class has the same birthday. It's minus 30 and then the plus 1 because the first one, the 365 itself, is 365 minus 0. But that accounts for one person. There are only 30 people. So the last one has to be 365 minus 29.
Is there a dot 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 in there? Is that like a series?
Yes.
Okay.
Yeah, sorry. Yeah, good point, good point.
Okay, that's what I needed.
Okay. Dot, dot, dot. Okay. So this one, when we generalize, we recognize that this 30 is representing the number of people in class, and then this one is representing k minus 1, where k is the number of people that we want, the minimum number of people that we want to have the same birthday. Is that okay? All right. And this number turns out to be, remember my mistake, okay? My mistake was to use combination when it's really just permutation. So this is permutation of 365, and we are choosing how many out of 365? It's really just 30.
Oh, because we want none of them have.
Right. It really is just 30 because we we cut that part off. Yep. Okay. So in this case, what is this? It's permutation of 365, and we know this part has to do with n, but we also know that we have to factor k into this. 30 is coming from 30 minus 1. So this n cannot be just n, it has to be, well, k has to be here somewhere, okay? Is it just minus k, or is it minus k plus 1? Okay. Minus k plus 1. Okay, so let's plug it in and see if it works, okay? K is 2 in this case, n is 30. 30 minus k is 28. 28 plus 1 is 29. So that's not working. Hmm? Yep.
I think it's the quantity k plus 1, as opposed to just k plus 1. You
Say
can
again?
change the plus in front of the 1 to a minus, or you can make it the quantity k plus 1.
The quantity.
So in parentheses.
Oh, parentheses, like that. Yeah. That makes it even worse, because if you that makes it worse. It's definitely the wrong direction.
What happened to
Okay. That part is not working. Okay. While in doubt, we check the first one and see whether that makes sense or not. Okay. The permutation of choosing 30 out of 365, does it make sense or not? It makes perfect sense, because that is telling us how many ways can we choose a different day, okay? 30 unique dates out of 365, and so that each person in class can have a different birthday. So it makes sense, okay? And we double check the math, the number matches with the answer as well. So we know that one works. Yep, go ahead.
That 30, though, that's just our k. I mean our n, excuse me.
30 is our n, correct.
So then we replace n with n minus k plus 1. Shouldn't it just be n?
I think it is n minus 1 plus Okay, if this is not working, then we work out the other one. Well, it's just one step at a time. Yep, go ahead.
Isn't k actually 0 over there? Since we said chance of no one in class having a 30.
So k is the number of people having the same birthday.
So in this case it would be 0, k equals 0.
No. K is the number of people having the same birthday, which means that's the k coming from the original problem. But by looking at the complement of the problem, if you don't want any 2 people having the same birthday, that means you want to have at the most 1 person having the same birthday. That 1 is coming from k minus 1. Is that making any sense? No?
Because k happens to be 2 minus 1, I mean, that's just number 9.
Okay, so if one step generalization doesn't work, let's do it another step first. Okay, so we'll still consider a class of 30. Okay, so this time we want to say what are the chances of at least 3 people having the same birthday in 30 in a class of 30. Okay. So that's the new question. Okay, so we're just stepping it up by 1. Okay. And obviously we can apply the same thing and say, okay, instead of looking at having 3 people, at least 3 people having the same birthday, we look at the flip side of the problem of at the most 2 people having the same birthday. Is that right? Okay. So we say, now recast the problem as the complement is at most 2 people having the same birthday in a class of 30. So we look at the complement instead. So we'll also use k, the designation of k here, so that we can easily refer these back as, okay, so that's our k. So in this case, this 2 is obviously, it is k minus 1. Does that make any sense? Because if I want to look at the flip side of at the most, at least 3 people having the same birthday, and I want to convert it into at most 2 people having the same birthday, that 2 is obviously 3 minus 1. It's just one fewer than the target number of people. Is that okay? All right. So what do we do about this complement? How do we compute this complement? This complement is now saying out of 365 days, the first person can choose any day, and then the second person can choose 364, and dot dot dot. What is the last number that we're multiplying? We only need, this time out of 30 people, we want 29 unique birthdays, because we can have 2 people sharing the same birthday.
So that's permutation of 365 and
Choose 29, right? So this is going to be the permutation of 365, choose 29.
Isn't it just n?
Hmm?
You can keep going.
But okay, but does that make sense? Okay, out of 365 days, we want to choose 29 unique birthdays. Is there anything else we need to do with this?
Don't you have to have 365 times 365 because 2 people have 3 choices of birthdays? Because if 3 people have to have the same birthday,
Right.
then one person just can't have the same birthday as 2 other people. So 2 people can have the same birthday, but just one person has to have.
But we're looking at the flip side now. We are counting the frequency, or we're counting the number of outcomes, where at most 2 people have the same birthday within those 30 people. Yep.
So now we need to add the possibility of one person having one birthday out of those 29.
So if we want k people to have the same birthday, we basically aren't we gonna take k people outside of our total unit, and then those remaining n people hypothetically can have whatever birthday they have?
We're missing a number here, okay? I just want, okay, go ahead.
I had a thought. I feel like I'm right, but I might not be. So
Go ahead.
I was thinking it'd be 365 days times 1 to the k, because you've got that many people, and then that brings you to 365 minus k to the n minus k would be the total number of cases of just that amount of people. Does that sound about right? So 365 basically to times 365 minus k, the quantity to the n minus k, because you've got that many people left, and you have to do 365 minus k because you've got to account for the 2 birthdays that are the same, but not, because they can't have 365 days to choose from, they only have 365 minus k.
So in that term, 365 29, that's 29 unique birthdays.
Yes.
Right. So the possibility of at the most 2 having the same birthday means that we're looking for another person that shares one possibility of that, or one day. So we have 29 distinct days.
Yes.
So the 30th person will have one of those with 29.
That is correct.
So that's
So this number is correct.
but we still need to multiply it. I'm not sure.
Okay, what are you going to multiply this with?
The possibility is the possibility of one person having one birthday or one birthday out of those 29.
This will be this will count the number of chances where exactly two people having the same birthday.
So we need,
So we want at most two people, so we are not counting where everybody has a unique birthday, which is the probability from the first one.
The results are in.
Okay.
There are 2 people who were born on July 28th and 3 people who were born on July 17th.
Oh, wow.
I don't know if it's correct.
Out of 45 students.
What if you get the K over 365 permutation pick n, all over 365 permutation pick n to the power of k?
I'm gonna cheat.
Is that what we're gonna
That's
do?
about
That's
time.
right. We can do that on the test,
Open note, open Wikipedia.
Just gonna look at the closed form first.
Yeah, that's the one that was original.
What is okay? Pn is permutations.
365 big n permutation n is the chances of all the permutation of everybody's birthdays. So chances for all of the possibilities. That's a pool. It's not 365 with the power of n. Is that
I think these are still looking at 2 people, and I mean, having at least two people having the same birthday, because I don't see a K here.
And doesn't it really actually think about how many?
Check the table of contents, maybe they go into it.
Or see if anybody took it out recently.
I'm not gonna.
Okay, let's look at the problem that we are solving. Yeah, it's really just at least one pair, so they have never generalized it.
there was a generalization section.
Okay.
In fiction.
In fiction, yeah.
Generalization.
621. Okay, so the generalized problem is n randomly chosen people, and we have D people sharing the same birthday, I guess. Given a year with D days, okay, but that's not helping either. Right?
I'd like to think it's
That's the last thing we needed to generalize is the number of days in a year.
Yeah, that's what is generalizing. Well, at least that's what I'm seeing here. Okay, so maybe they haven't really talked about the generalized form. Okay. So cheating did not really help in this case, does it?
Does it ever?
when it's not like this, it can.
So is this gonna be on the test, or?
Well, I guess I'm sure on this a little bit more. We'll move on to some other questions. Yep.
I was just wondering on the previous question. Permute 365 and 629, are you saying that no one having the same birthday?
No. Okay, so you have 30 people, right?
Right.
If you have 30 people and you only have chosen 29 unique birthdays, okay? What kind of situation do you have?
Yeah, where one.
Using the pigeonhole principle, what does that mean? What is that implying? Now I think I'm pretty close to finding the solution of at least 2. It's just I haven't found a closed form yet. Okay. What is this representing? 365 choose 29 in terms of permutation. What is that number representing? It's representing the number of outcomes, but what am I interested in with this number? Exactly 2 people. Okay? Exactly 2 people out of 30 people have the same birthday. That's the number of outcomes for that particular problem. Okay? But if my interest is at the most 2 people having the same birthday, this is only a part of it. Because I'm forgetting The other part. The
You
other
got to
part
divide by the number
that
of
we have
combinations.
already talked about.
You got to divide by the number.
Well, we have to divide it too, but we are forgetting this one.
Yeah, it's a good percent.
We are forgetting the number of outcomes where everybody has a different birthday. So these two, is there a chance that these two will overlap?
Where everybody's birthday and
One is representing the cardinality of the set of everybody having a different birthday within 30 people, whereas the other one is representing the cardinality of the set where exactly 2 people out of 30 have the same birthday. Do they overlap? They cannot overlap. They're disjoint. So if I want to compute the cardinality of the union of those two sets, I can just do addition to these two numbers. Is that making any sense?
Yeah.
But isn't that combined number the complement of what I want to figure out?
you shook your head out.
Because I want to find out how many, what is the probability that at least 3 people have the same birthday. I have just ruled out 2 people sharing the same birthday and nobody shared the same birthday. Yep. So that means, now I know this is not a closed form, it does look a little bit ugly, but this number is what we're looking for. Okay, 365, 29, 365, 30, and then this number, okay, 1 minus, this number is, the bottom is still 365 to the power of 30, because the total number of outcome does not change. When you have 30 people, there are always 365 to the power of 30 possible outcomes. Okay, so the denominator cannot change. It's the numerator that is going to be changed. So this number, okay, the one that I just wrote, is representing the chances of at least 3 people having the same birthday in the class of 30. Okay, conceptually, does it make sense? Is this number smaller than the number that we just looked at, where 2 people, at least two people share the same birthday?
Well, we didn't have that.
Yes. Yeah, exactly. We added one more component in the portion that we are subtracting. So this has to be a smaller number, which makes sense, right? And if we continue doing this, this chance will get lower and lower and lower as we say, okay, at least 3 people, at least 4 people, and so on. Yep.
Going back to at least 2 people, would the difference between that and 3 people would just be that instead of adding the plus 365 choose 30, it would just be 1 minus choosing, or e 365 choose 29 over that number. So the only difference is that you added a second option basically for the at most option.
Yeah. Yep.
What if you just do a sigma notation for going from
Yes, you can use a sigma notation. Okay, what is the extreme case? Since we have a class of 30, so we can say at least 2 people having the same birthday, at least 3 people having the same birthday, at least 4 people having the same birthday. What is the extreme? What is the other extreme? Everybody have the same birthday. Okay. Now that one is easy to calculate as well. Yep, go ahead.
So if we're thinking of at least 4 people having the same birthday, this is going to expand, or just have, instead of 29, it's going to be 28. Be 365 28 plus 365 30.
If we want at least 4 people having the same birthday, then we have to add P 365, 28 to the numerator, because then we have to exclude nobody having the same birthday, exactly 2 people having the same birthday, and exactly 3 people having the same birthday.
So we're just adding another.
We are just adding some more terms.
In numerator.
Okay? So that means, okay, so that means when you try to say, okay, what if I want the entire class to have exactly the same birthday? That is going to be a number that looks like this, right? Okay, this number is representing nobody in the class has the same birthday. At least exactly 2 people having the same birthday. Exactly, let's see, nobody shared the same birthday, 2 people shared the same birthday, 3 people share the same birthday, and we add everything up to what? the summation is going to end with, well, that number will continue to decrease, but it cannot decrease all the way down to, okay, does it decrease all the way down to 1 or down to 0? We start with 30, and it goes down to 1. And then that number divided by 365 to the power 30, this number is going to be representing the chances of everybody in the class having the same birthday.
Since you mentioned it for labs and videos, can we see that in Sigma notation?
In Sigma notation?
Yeah, what would be that series?
In Sigma notation, that's going to be,
Because we can just turn the P into like n factorial over.
yeah, the summation is going to be a variable I going from 1 to 30, P 365 I, and then the summation is still 365 to the power of 30. Does that make any sense? In fact, once we have the summation notation, we can now replace the 30 with K, which is the minimum number, which is the number of people having the same birthday. At least that many people having the same birthday.
Then 365 to the power of K.
Huh?
Then 365 to the power of K.
To the power f of n, actually. This is n.
So
Because the denominator is only determined by the number of people in class, but not the number of people having the same birthday.
Shouldn't it be n minus I?
N minus I.
If it's 30, then it works, right? But for the general form, you want n minus I, not I.
Oh, right. Okay.
Well,
So we technically just found the general format then using the sigma notation.
That's correct. Yep.
Cool.
So
N minus I
I
plus
feel ready
1.
for
see, that's why we always do math, man. Just, well,
That part is n minus I plus 1.
Or if you start I at 0.
Yeah, you
then
can change I to.
okay.
Yeah, but since K has a special meaning, I have to go up to K. All right. So I guess someone can verify this, and then we can extend Wikipedia.
But this assumes that each birthday is equally likely,
That's correct.
which is not true.
Exactly.
But it doesn't look like it's this simple.
At this rate,
Okay.
we can have
It
the
follows
test
a Poisson
in spring.
distribution.
Poisson distribution.
Yeah, it has more to do with that. And it doesn't look, I mean, the case is really complex in here, but and there's a paper that someone listed on here as well that does a really, I mean, I can't really even say the function out, but it's
Okay.
such a long function, but I don't know if it's.
Has anyone taken statistics and know what is Poisson distribution? What is Poisson distribution? It looks like Poisson, but it's not. Huh?
He said that's a good question.
You said it's a good question. Okay. Poisson distribution doesn't fall into the curriculum of this class for one reason. The title of this class says it all. Discrete, because Poisson distribution is actually continuous. It's not a discrete probability. This is still discrete because we can still count the number of outcomes. As long as you can count the number of outcomes, then it is discrete. The Poisson distribution actually has to do with what are the chances that it's a frequency kind of thing. Okay, what are the chances that something will happen within a certain amount of time. That's the Poisson distribution. If I remember correctly, that was a long time.
You can approximate discrete into Poisson.
Yes, discrete and continuous definitely has a correlation because when you look at the binomial distribution, you guys still remember binomial distribution? Poisson, the Pascal triangle thing? If you go all the way down or keep going down and you plot out the actual frequency, you will see that the curve increasingly becomes smoother and smoother, and it will become closer to the normal distribution. So discrete and continuous definitely has a correlation because I think it's in that case it's basically an approach kind of problem. As n approaches infinity, the binomial distribution approaches the normal distribution. Okay, so we went through one question. Let me just kind of go through all of the other questions in
a minute and a half?
in minus something minutes. We just have to warp time a little bit.
Well,
Okay.
I mean, assembly's not that important, right? It's just
Yeah, exactly. We'll take the break time. Because either you go home, because I don't think there are any other classes than CISP 310 after this one. So either you go home or you have to stay here for my next class anyway. Right? So we can just queue up a few more minutes. Okay, question number 3. Assume an even point is used in tossing. What are the chances exactly 4 out of 100 tosses are heads? Exactly 4 out of 100. That's binomial distribution. Okay, so you just have to look up binomial distribution and figure out, the probability of that one. Question number 4, using proof by induction, prove that n factorial is the summation of the product of n I equals to 1 to n I, and you are given the definition, the recursive definition of factorial. Okay, so that's a proof type of issue. We can go. We will get over this on Thursday. Okay, so we will do. I'm not really pushing all the questions in a few minutes. Yeah.
If you don't get it done, like reviewing on Thursday, will you extend the exam?
Yeah, we'll get it done. That's cool. Question number 5. Okay, question number 5 is the one that I think is the most fun. The following is one way to implement string compare. Okay, so I do give you the actual assembly code to do string compare. I want you to re-implement string compare recursively. Okay. Once you know how to do one, the other one is going to be easy. And then question number 6 is a model problem. Okay, and all the model problems fall into one way to look at things. So I don't think that one is going to be too big of a deal. All right, so those are all the questions. I don't think you would need a calculator for anything that is difficult to calculate. You can just give me the equation itself. Then you don't have to go through the actual calculation. Okay. All right, I'll see some of you on Thursday, and the rest can take a break.
Is that one the practice right here, or is that the?
This is the practice.
Okay, good. Yeah. That'd be nice if the actual we can get the answers.